Previously, we are using these two ways to improve the derivative and integral estimation. We can either decrease the step size or using the differentiation or integration with higher order formula in order to improve the approximation. Besides this method, we can also use the Richardson extrapolation to obtain a more accurate estimation. This method requires two derivatives or two integrals, one with data with step size h and another data with step size h over 2 to obtain the result. So this is the Richardson formula for the differentiation and integration. In this formula, two derivatives here and the two integrals here are the old estimation. The former number is equal to j and the later number is equal to k. K number here means the accuracy level. For example, if you solve the integration by using the trapezoidal rule, so the error will be OH2. Both of these numbers has k equal to 1, therefore they have the same accuracy in terms of the algorithm. J number here means the sample of the derivative or the integration. Besides that, j plus 1 will be always have half step size of the j. For example, let the j equal to 1 in this case, then j plus 1 will be equal to 2. So I21 here has half step size compared to the I11 here. After you compute this formula, you obtain a new integration result which is in I12. So 2 here means that you have a better accuracy in terms of algorithm, where previously you have OH squared. So after you perform the Richardson method, then you obtain OH power 4. You see that you can improve the differentiation and integration result by using the Richardson method. So these two formulas are the same. You just change to the symbol D to represent the differentiation and you change it to I to represent the integration. We can further improve the differentiation and integration result by using the Romberg differentiation or the integration algorithm. So this algorithm is an extension for the Richardson method. Where you can see over here, the formula are almost the same, just that we have 4 power of k minus 1 here. So the front number here is equal to j plus 1, the later number here is j, and since these two has the same level accuracy, therefore you have k minus 1, and after you perform it, you obtain the result in k, and this is your j. So 3 here is equal to 4 power of k minus 1 minus 1 here. So this formula is for the differentiation. If you want to apply it on the integration, just change the D symbol to the I. Then this is for integration purpose. Since the implementation of these two formulas are the same, let's just stick with one example here. So let's say in this case, the original implementation is by using the trapezoidal rule, where we know this method is OH squared. So you find the solution by using h equal to 1, then you will obtain the integration result for I11. Then you continue to perform the integration by using h equal to half of it, then you obtain I21. So these two integration result is the old estimation as shown here. Substitute inside this formula, then you should obtain a new estimation by using the Richardson method. So I12 is the new result, then from these two terms you can obtain this result. So this is the first iteration in the Romberg algorithm. For the second iteration, you choose h equal to 0.25, which is half of the previous step size, and then you obtain the integration to be I31. We can use the same formula to solve these two derivatives in order to obtain I22 here. So the old sample now is I21 and I31. I31 has better accuracy than I21 because the step size is lower, therefore we put it to here. So this is I31 minus with I21. After you solve it, you obtain I22, which is equal to this value. So you see that to convert the original integration result here to a better accuracy here, you let the k equal to 2 in this formula. So if you substitute k equal to 2 inside, so 2 minus 1 here, you have 1, 4 power of 1, you still obtain 4. So this one will be 4 also. 4 minus 1, you obtain 3 here. So k is equal to 2, 2 minus 1 here, you obtain 1. 2 minus 1 here, you obtain 1 as well. When we compare this algorithm with the Richardson method here, is exactly the same. Now we have 2O derivative at the accuracy k equal to 2 here, and you want to convert to I13, which has accuracy k equal to 3. To solve this answer, you need to substitute k equal to 3 inside the Romberg algorithm. So when k is equal to 3 here, 3 minus 1, you obtain 2. So this will be 2 as well. So this is the new algorithm to find the answer here. So you have the O estimation at j equal to 1 and j equal to 2 here. So j plus 1 here will be 2. J here is 1. Then you obtain the solution for I13 here. So this is your second iteration. At k equal to 2, you have the solution with h power of 4 here. At k equal to 3, you further improve the accuracy and you have OH power of 6. If you are not satisfied with the integration result obtained here and you want to further improve the accuracy, you can continue the calculation by using this Romberg algorithm. So you can continue the iteration for k equal to 4, 5, 6 and so on. You can set the stopping criteria by using the approximate percent relative error. When the approximate error that is computed by using this formula less than the stopping criteria that you set, then the iteration will stop. For example, for the first iteration, you are using these two derivatives to obtain the new derivative here. So this is your current result minus with the previous result here divided by the current result here and multiply with 100%, you obtain the approximate error for the first derivative. Check it with the stopping criteria. If this error is less than stopping criteria, then you continue for the second iteration. In the second iteration, you are using these two integration results to obtain new result here. So this is your current result. So you take the current result minus with the previous result here and divided by the current result, multiply it with 100%, then you obtain the approximate error at second iteration. Then you compare this approximate error with the stopping criteria. If this approximate error is less than the stopping criteria, then this is your final result and the iteration is stopped. In the previous example, you have used the numerical integration method to obtain the integration result for this function from the limit a equal to 0 to 0.8. For example, you are using the trapezoidal rule with different step size from 0.8 to 0.1 here. By using the trapezoidal rule, so this is your original estimate with the error equal to OH square. So this is the integration result at different step size here. Since you have the lowest step size here, therefore this integration result is the most accurate result that you obtain among these four samples. You can further improve this accuracy by reducing the step size or improve the algorithm. Besides these two approaches, we can use the Romberg integration to improve the accuracy. First of all, you need to arrange the integration result from the higher step size to the lowest. And also you must ensure the next integration result has half of the step size compared to the previous integration result. This is an important requirement for the Richardson method used in the Romberg integration. In the first iteration, you have the k is equal to 2. By using the 2 sample here, substitute inside this formula, you should be able to obtain new integration result. For the second iteration, you have k equal to 3. you continue with these two integration results, substitute inside this formula, then you should obtain the new integration result to be I22 here. Then you continue for these two samples here, substitute inside this formula, then you should obtain I13 here. For the third iteration result, where you have k equal to 4, so you start from these two samples, substitute inside the formula, you obtain I32 here. Then you continue with these two samples, substitute inside this formula, you obtain I23 here. Lastly, substitute these two samples inside the last formula, then you obtain I14 here. You need to be careful, we are using three different formulas here. So we have this formula when you select k is equal to 2, by convert the original estimate with OH power of 2 to OH power of 4. For these two formula, you select the k equal to 3, where it converts OH power of 4 to OH power of 6. Last formula, you use k equal to 4, which convert the OH power of 6 result to OH power of 8. So this is the notation for the I symbol that you use in the formula, where you can see the integration result can be arranged in a lower triangular matrix. The number at the column here is equal to k. For example, at the first column, you have the later number here all equal to 1. So first column is equal to k equal to 1. Second column, you have k equal to 2. Third column, k equal to 3. And fourth column, k equal to 4. And you use the symbol J for the row here, where you have the J equal to 1 indicate the first sample, J equal to 2 indicate the second sample in second row. So this is the third sample and fourth sample. In this example, we success to use the Romberg algorithm or the Romberg integration to improve the accuracy of the integration here. And this is the final integration result that you obtain from the Romberg integration. You can see the result here is saturated at these four results. The integration result remains constant after the second iteration. Therefore, we are confident that the integration result is accurate up to 7 significant figures here. You can see the accuracy level of the integration result increase in a very fast manner from OH power of 2 to OH power of 8. Compared to the approach to increase the accuracy by reducing the step size, Romberg integration is more efficient to compute an accurate solution. In this example, you have two derivative results at the step size equal to 0.5 and 0.25. Assume that these two results are given in advance, then you need to improve the accuracy of the result by using the Richardson extrapolation. So this is the formula for the Richardson method. The derivative result at D21 here has better accuracy compared to D11. And the step size for D21 must be half to the step size of D11. So the step size for this derivative result is larger and is more than this derivative result by 2 times. Therefore, this result is your D11. And this result will be your D21. Substitute it inside this formula, then you obtain the D12. This result has k equal to 2. Compared to the previous derivative result, you only have k equal to 1. So k equal to 2 has OH power of 2 in this case, because the original estimate here you have OH. After you perform the calculation, then you should obtain this result. Since the example here is only required us to use the Richardson method, therefore this is the finalized result. In actual, if you want to further improve this derivative result, then you can further obtain the D0.125, which is half step size of the previous derivative result here. So you can continue apply the Romberg algorithm to improve the accuracy.